Ready for
Sure.
countdown? All right, I'm gonna start. So welcome to the CC Colloquium for this week. We're very pleased to have Craig Hardgrove, our very own Craig Hardgrove, giving a presentation on his exciting mission. Before we do that, Miniwado, I wanted to say a little bit about next week's community conversation. So Mini, take it away.
All right, thanks very much, Ariel, and hope everybody is doing well at this point in the semester, and everything's going great for your classes or for your research, whatever you're engaged in. I just wanted to highlight the fact that our community conversation, which we had been having on a monthly basis over the summer during colloquium time, we're going to continue that this semester, but we're not going to be doing it at the colloquium time. So I just wanted to make special mention of the fact that it's going to be held between noon and 1 p.m. next Thursday. So it's going to be the last Thursday of the month, and hopefully you can join in, and we'll be following a similar format to what we've done before, with Ariel presenting some of the update on COVID. And then we'll talk a little bit about what's going on locally and at ASU. So anyway, that's about all I have, and have a great colloquium.
Thanks. Somebody is asking where they can get a Zoom link to that. So I assume you'll be circulating a Zoom link to that conversation next week, I guess.
Right. So actually, Kim Baptista will be sending a notice, a flyer about that, hopefully this Friday with a Zoom link. So keep an eye out for that, please.
Great. So with that, Jim, I'm turning over to you to turn over to our own Jim Bell to introduce our own Craig Hardgrove.
Okay, thank you, Ariel, and it's great to virtually see everybody out there. I miss our getting together for colloquium, but I'm glad that we do keep it going. We've got a great one today. Delighted to introduce our own CC colleague, Craig Hardgrove, who will be talking about the LunaH-Map mission today. Craig is an assistant professor here in CC. He got his PhD back in 2011 at the University of Tennessee, his bachelor's in 2004 from Georgia Tech in physics. He's an expert on nuclear spectroscopy. So he promised tons of equations having to do with neutrons and gamma rays in this talk. I'm looking forward to that. But he's an expert on spacecraft instrumentation, become an expert on spacecraft instrumentation because of his experience as a principal investigator of the mission that you're about to hear about. And this mission was ASU's very first entire mission. Tiny, as you'll hear about it, but mission nonetheless, selected competitively through NASA's Simplex program. Craig is involved in a number of other missions. He does field work, he does theoretical work. He works on the Curiosity Mars rover on the dynamic albedo of neutrons team. He's a participating scientist there. He's a co-I on ASU's own MASCAM-Z team on the Perseverance rover. He's one of our lead liaisons between the camera team and the radar team, the ground penetrating radar team. So he's got a lot of, and building a lot of experience with NASA missions. And this mission is no exception. You're going to hear a fascinating story and a fascinating talk from a fascinating guy. So welcome, Craig. Take it away.
Thank you so much, Jim. Thanks, everybody. So yeah, I'm going to talk about LunaH-Map today. And this is a picture of the spacecraft. It's the size of a large shoebox. This may or may not be, it's certainly close to the smallest NASA interplanetary mission that's ever been built. And it contains, you can see there close to you is the propulsion system. We have a deep space radio, reaction wheels, star trackers. Those solar arrays are gimbaled so they can rotate. We have a full set of batteries to keep our cells charged. And there's a neutron spectrometer that's the main instrument on the spacecraft that will be making measurements of the hydrogen abundance at the lunar south pole. And we use hydrogen abundance as a proxy for water and water ice on the moon. There's been a lot of evidence over the last several decades that there are enrichments of water ice at the south pole of the moon. And some missions that have been sent before are unable, just due to some of the mission constraints, to really constrain the spatial distribution of that ice. And as you probably have seen, there's a lot of interest, renewed interest in lunar exploration over the last few years. And we are manifested on the Artemis 1 mission. So the very first launch of NASA's new SLS rocket will launch LunaH-Map and a set of other CubeSats into deep space to conduct their own science investigations. I wanted to start this was something that came out not too long ago. NASA Science Mission Directorate releases what's called a fleet chart. So you'll see some missions that we're very familiar with here, like the Perseverance rover, the Curiosity rover, and Psyche, as well as the Lunar Reconnaissance Orbiter. And in the section for the moon, I was very happy to see that LunaH-Map is now officially part of the fleet. So we may be a dinghy as part of the fleet, but we're a very small mission that contributes to the overall science goals of the Science Mission Directorate at the moon. And it was pointed out to me by several people that this is not at the correct scale. As Jim and I have both mentioned, LunaH-Map is very small. So I did a little bit of measuring in comparing ourselves to the Lunar Reconnaissance Orbiter. And that's about as close as I could get, just so you can see our actual size in comparison to LRO. Not quite microscopic, but we're again a very, very small 10 by 20 by 30 centimeter spacecraft. When the solar arrays are deployed, they extend to about a meter wide. So rather small, and so many things on this mission are new. And as Jim said, this is a new type of mission for NASA. There's a program called Simplex, Small Innovative Missions for Planetary Exploration, the calls were released in 2014, and we wrote a proposal to address the science goal of identifying how much water and exactly where it was located to within several square kilometers at the lunar south pole, using this new CubeSat technology. So if you're familiar with CubeSats, I'll just go through a bit, and please bear with me, but these are some of the very first space CubeSats that were successful. These are the size, they're 10 by 10 by 10 centimeter cubes. And the creator of this form factor actually said he created them to be mostly useless as engineering demonstrations. So he's a university professor, and engineers love constraints. And what better constraint than to build spacecraft components into a very small box. And he came up with it because he had a granddaughter at the time, and he was looking around and saw a Beanie Baby box on his desk next to him, and thought that was a great small size. I know Beanie Babies aren't popular anymore, but they were at the time 15 years ago or so. And so that's where the form factor came from. And it was really intended to just be an engineering instructional exercise for students in engineering schools to develop the technologies, power systems, solar panels, battery systems, star trackers, reaction wheels, all those components, and just to put them into a very, very small form factor. And so these are called phone sats. They were developed out of Stanford, and they actually have a cell phone camera, magnetotorquers, all various components that you would use to operate the spacecraft, a radio, antennas, and they were successful at taking pictures in Earth orbit. And people did not think this could be done using off-the-shelf technology. They didn't last all that long. The pictures were not outstanding, but they worked. And so since then, we've been refining these technologies. And so they started out as these one-use 10 by 10 by 10, and they've grown. And so these are 3Us, 2 or 3Us that are being deployed from the International Space Station. So there's a deployer on the International Space Station that you can, universities can develop their CubeSats and have them deployed. Then LunaH-Map hardware will actually be deploying in November, sorry, as a test demonstration of some of the neutron detector technology that we're using in low Earth orbit on one of these opportunities. And I know others, the Phoenix CubeSat was recently deployed from this deployer as well. And so it's a great tool for benchmarking and testing new technologies that fit within this very small form factor. And we heard from, I believe last year, Andy Klesch, who's the PI of a mission called Marco. And this is the 2 spacecraft that flew alongside the InSight lander that landed on Mars. And the purpose of those spacecraft was to relay the entry, descent, and landing data from InSight back to Earth. And they deployed from the primary spacecraft in transit to Mars, and they were free flying on their own. They had their own small propulsion systems and radios. In fact, they're using the same radio that we're using on LunaH-Map. And they were able to relay the entry, descent, and landing data successfully from InSight back to Earth before the Mars orbiters were able to tell us about the success of InSight's landing. And so these 2 little CubeSats, the same size as LunaH-Map, were able to operate successfully at Mars, and they're now out beyond Mars orbit. And hopefully, when they get a little bit closer to the sun and they can charge their batteries, we may or may not hear from them again. But this picture was taken by the Marco spacecraft as it departed Mars. And the reason, it's just kind of an interesting tidbit I read, the reason they offset Mars on purpose was a little bit of to demonstrate or have people think about what might come next for these spacecraft. They've come to Mars, and now they have this big black empty space on the left side for what can we do next. And so Andy was quoted as saying, Marco is heralding these new things to come, and they may not be better things, but they're different. And it's a new way of exploring space that's going to complement all of them, hopefully, all of the missions that NASA conducts. And so in 2015, NASA selected the LunaH-Map proposal for flight, and we are destined for the moon as part of the Artemis 1 mission, and we'll map the hydrogen deposits at the South Pole, which I'll talk more about in a minute, at spatial scales that will help us resolve the distributions of the hydrogen within and outside these permanently shadowed regions. And in order to do that, we have to do things a little bit differently than Marco. We have to operate for a long time in deep space. Marco had to operate for about 9 months. We have to operate for a little bit longer than that, and we have to execute many more hours of propulsive maneuvers in order to get ourselves in orbit around the moon successfully. And so we have a small propulsion system, which I'll show you some images of, that we have to operate. You can see the deployer ring. So that's the SLS, first build of SLS. They'll change it for subsequent launches. And there are the CubeSats, the number of CubeSats in the, it's called the interim cryogenic propulsion stage that deploys underneath the Orion capsule. And then after the Orion capsule is deployed and does a figure 8 around the moon and comes back to Earth, those CubeSats will all be deployed in sequence, and they execute their own missions. And I wanted to spend a little bit of time because I personally think it's interesting when we talk about small missions, just to think about what does it mean to have a small mission? The obvious thing that you think about when you think of a small mission is that the components are tiny. Our propulsion system is about the size of a tissue box. That's cool and interesting, and it has to be very new technology. But the thing that I personally live, and many of us live day to day on the mission, is not so much the difficulty in working with tiny hardware. It's the tiny budget. I think that it's when people think about CubeSats, you can build a Class A CubeSat or a Class B CubeSat. I have this chart that the Psyche mission put together. It's a wonderful chart to describe the different mission classes, Class A through D. And I put just some notional mission total life cycle budget for Class B and Class D missions. LunaH-Map sits somewhere around $15 million. So we're not Class D. We're somewhere beneath a Class D mission, and there are no definitions for that type of mission. It doesn't mean that we'll be any more or less successful. We're doing everything we can. As you saw, Marco is on the same scale of budget and was very successful. So we're trying to define what's an acceptable level of risk for a mission that's subclass D in the NASA profile of missions. And there are other challenges in addition to the budget and the components being very small. Some of the parts are new. So NASA has not needed to make a propulsion system that's at that size and mass and power. And so we need to come up with, and we've done a series of tests that build a sufficient level of confidence for our mission that component will execute the mission that we need it to, as well as all of the other components on this program. It's not the type of program that you would see on Class B, certainly not Class A, even Class D missions, but we test the critical mission scenarios that need to happen to execute a successful mission. We think, or I personally think, this is my editorial, that these types of high risk, high reward, very small missions have a place in NASA's science mission profile. They don't require a dedicated launch. And if you keep them simple with a single instrument and highly focused, they can lend themselves towards these multiple mission opportunities. And the science component to it, which is what makes our mission different. We're on the science mission fleet chart. There are 12 other CubeSats on Artemis 1 that are technology demonstrations primarily. And I've found over the last few years working on LunaH-Map that emphasizing the science mission helps push the technology because we have a science mission that drives the entire goals for the mission. We're pushing the propulsion system and all of the other components to support those science missions. And if future missions will do the same, they have an overarching science goal, as opposed to being a technology demonstration where it can be very easy to say, well, let's turn on the propulsion system, and if it works, we can declare success. In our case, that's not good enough. We have to turn it on and make sure that it can execute our science mission. So I really do think that there's a good place for these missions in the overall profile of NASA missions. And so the risk in these missions is baked in. As I'll talk about, LunaH-Map needs to fly very, very low over the south pole of the moon to make meaningful neutron measurements of ice at the South Pole. And so because of that, everything flows from it. Lunar Prospector could have flown that low, but didn't. Lunar Reconnaissance Orbiter could potentially fly that low, but they don't, because there's a lot of other components and investigations on that mission. The overall mission is just much different than LunaH-Map. So the risk is baked into these types of missions. And I think if we continue to see these high risk, high reward missions, it'll be an exciting type of mission for NASA to pursue in the future. And we lean on heritage. So low Earth orbit components that have flown, and Marco has really led the way for us in many of our flight components. I'm going to try to play a video here if I can. And it's just on the Artemis 1 mission and the CubeSats. So let me disable my headphones and hopefully you guys can hear this.
NASA is advancing science and technology with the first flight of the Space Launch System, or SLS. Demonstrating the capability of the new rocket and the Orion spacecraft in deep space for future human exploration is the primary goal of the mission. As a bonus, SLS will send small satellites called CubeSats to deep space destinations where they can gather valuable data for future exploration missions. Once in orbit, the SLS upper stage, called the Interim Cryogenic Propulsion Stage, fires its engine to propel Orion toward the moon. SLS will send Orion farther out beyond the moon than the Apollo astronauts traveled, where it can test communication, navigation, and other deep space exploration systems. Once Orion is a safe distance away, the fleet of 13 CubeSats will be deployed. The onboard avionics box will command each dispenser to release the small satellites, sending each one on their way to deep space destinations such as the moon or an asteroid. Each has a mission that can provide NASA with new key knowledge and test new technologies. CubeSats flown on the mission will perform in-space experiments and demonstrations that will actively advance the capabilities needed to take humans farther into space than ever before.
Okay, so yeah, NASA put that together. Hopefully you guys can still hear me.
Yep.
Okay, great. So water on the moon. This is not what we expect to find. It's just, it's fake. There is not ice skating rinks at the moon. We expect that the water that we might find is bound or adsorbed in the lunar regolith, in the lunar dust. And we believe, again, not this, that it's primarily concentrated in these regions of permanent shadow. This is an LROC image, an actual image that was taken of the moon. And on the right side is the interior of a permanently shadowed crater at the south pole of the moon. And that's a place where we believe that the ice would be stable. There's no atmosphere to speak of on the moon. And so the temperatures are some of the coldest in the solar system. And they get cold enough that we think that ice can be preserved in these regions. And we're fairly certain that it got there from passing asteroids and comets depositing water ice, and then that water ice being remobilized on the surface. Some of it escapes due to micrometeorite impacts and other impacts, and some sublimates away. But mostly it will, some of it will eventually mobilize and get trapped in these cold trapped regions, in these permanently shadowed regions at the South Pole. So the thermal environment has been well characterized at the South Pole from the Diviner instrument. It's a thermal radiometer that is in orbit on LRO around the moon. And so these are some of the winter average temperatures at the South Pole where LunaH-Map will be flying over. And you can see some of these regions are really some of the coldest in the solar system. And may, in some cases, may have never seen light before. So passing delivery of ice by comets and asteroids and migration of these hydrogen-bearing species that are implanted by solar wind into these cold traps really concentrates the material in these regions. There's also been some thermal modeling done based on ice stability, which shows these regions in white at the South Pole are where we would expect that ice would be stable at the surface, but there are other regions that are outside of those white regions that are in green and red, where within the top meter of the lunar surface, we would expect ice to be stable. And so from the perspective of our instrumentation that we have in orbit, we should be able to detect that. And in this case, we can detect in some regions with the instrument called LAMP. It's a UV spectrometer that's detected evidence of frosts, of ice-rich frosts in some permanently shadowed regions, but not others. And in this case, we sent, this is a map from a neutron spectrometer that was sent on Lunar Prospector. And this shows the integrated hydrogen abundance down to a meter at the lunar South Pole. And you can kind of page back and forth between the frost distribution and the neutron the hydrogen distribution from neutrons. And you can see that they're not entirely consistent with one another. The regions in red here, by the way, are just regions of permanent shadow. And so the regions of permanent shadow at the South Pole do not always show enrichments of hydrogen and the bulk with neutrons down to a meter, and some don't show enrichments in frost. And so there's been a bit of a discrepancy between these data sets. With neutron data, they're not spatially, it's not an optical instrument. So the spatial resolution of a neutron spectrometer is about 1.5 times our orbital altitude. So in the case of Lunar Prospector, the South Pole orbits were at a minimum around 30 kilometers. So the spatial footprint is around 45 square kilometers. So we're not resolving specific features necessarily, but you can, if you get low enough, resolve permanently shadowed regions. So what was done with the Lunar Prospector data was a spatial deconvolution to say, well, assuming that the neutron counts the neutron count suppressions came from regions of permanent shadow, and only the regions of permanent shadow. That's where the hydrogen is enriched. You can approximate the distribution as in the map that you see here. And so in that case, at Cabeus, which is in the upper left, you can see gets up to around 1,000 micrograms per gram. That's not milligrams per gram, it's micrograms per gram, sorry. But in other cases, it's sort of sitting at around 500 or so. But that's an assumption, that's a model-based assumption, and we don't know that hydrogen is only enriched within the permanently shadowed regions. And in fact, from the thermal modeling, we believe that there is evidence that there should be ice stable in the top meter elsewhere outside of permanently shadowed regions. And so you may be familiar with another mission called L-Cross that actually had an impactor. It slammed into Cabeus, kicked up a plume, and in that plume, they observed 5 weight percent. So that's 5,000 weight percent hydrogen in the plume of lunar dust that got kicked up. And so this suggests that the hydrogen distribution at the South Pole and the volatile content is perhaps heterogeneous at spatial scales that are smaller than what the neutron detectors that we've sent previously are able to detect. And so here's that same neutron map again, just with the permanent regions of permanent shadow shown on the right. And you can see that in some cases, there are small regions of permanent shadow around Cabeus and the L-Cross impactor, but we see significant neutron suppressions and enrichments of hydrogen in micrograms per gram in those regions. But we also see sort of in the region above Haworth, I'm kind of mousing over, I don't know if you guys can see my mouse, but there are some enrichments that do not correspond to any significant or laterally extensive regions of permanent shadow. So there are areas where the neutron signal that's observed from the relatively high altitude of Lunar Prospector is integrating large areas of potentially permanent shadow or large areas that contain enrichments of water ice. So all this points to the need for higher spatial resolution neutron measurements. On the left side, NASA did send an instrument on the Lunar Reconnaissance Orbiter called LEND. And this is one of the maps from LEND. The intention of LEND was to use a collimated neutron spectrometer to fly from 50 kilometers or so altitude and collimate the neutron signal from the surface of the moon. The results from the instrument are continued to be debated, but I just bring up this slide here to show you the maps that I already showed, the thermal stability of ice at the surface and this spatial deconvolution of the neutron signal, just to point out that these 3 maps do not match. And trying to understand why they don't match is the subject of what LunaH-Map hopes to address. And you can see here in the limitations of the current data, I point out the frost map compared to the LEND hydrogen map for Shoemaker, Faustini, Haworth. That's that triplet of craters. And you can see that the hydrogen distributions at depth integrated across a meter do not match the frost distributions. And so here's where LunaH-Map comes in, and this is what we proposed was, here's one example ground track from LunaH-Map flying over Shoemaker crater, a relatively large PSR at the South Pole. And you can see that in our initial modeling, you can see the altitude dips down to about 10 kilometers over Shoemaker, and the contribution from the hydrogen, if it were enriched all within Shoemaker, gets up to about 80% of the neutron signal, which is significantly better than what was able to be achieved with Lunar Prospector. And so you can see a few different ground tracks here where we're looking at contributions from other permanent regions of permanent shadow at the South Pole. And so these are the regions that we intend to study with LunaH-Map. I've circled some regions on the right, which are areas where the Lunar Prospector neutron map shows enrichments, but we do not necessarily, or does not show enrichment. So there is a region in the upper right that does show an enrichment in the neutron map. And then in the lower left, we do not see an enrichment in hydrogen. And yet there are laterally extensive regions of permanently shadow in those areas. So we believe that if we can increase the spatial resolution of these maps, we can discern exactly where these hydrogen enrichments are at the South Pole of the moon. And then these are our ground tracks. So this is the overall 141 orbits of the science mission that gets us the coverage over these craters, which will allow us to resolve the distributions. And then you can see here we can populate the South Pole with different amounts of hydrogen based on what's known. and we can propagate our orbit and our instruments over the South Pole, and we can show how well we can do. So this is if in 3 years or whenever Artemis 1 launches and LunaH-Map completes its science mission, this would be the type of map that we'd hope to produce from our 2-month science orbit. And the great thing here that we're showing is that you can see for Shoemaker, Faustini, Haworth, as well as Cabeus, we're spatially resolving those distributions from one another. And that's the real key. Whether or not we can reconstruct the actual hydrogen is difficult because we're still integrating a very large area. But we can show that the enrichment is within the permanently shadowed region or outside of the permanently shadowed region. That's something that previous missions are not able to do. So that's really the heart of what LunaH-Map is getting at. We can detect these expected hydrogen concentrations in PSRs. If the concentrations are larger than what we expect, we use the relatively conservative map here. If they're larger, we'll be able to see them better. Although they're not fully resolved in some cases, they're resolved, sorry, we don't achieve full contrast in all cases. And the low altitude enables us to have a high spatial resolution mapping and the surrounding areas of the South Pole. And the data can be used to understand how volatiles have been changed, how the distribution of volatiles has been changing over the course of the history of the moon. There's one theory that true lunar polar wander is the cause of the distribution of hydrogen, the changing distribution of hydrogen within these permanently shadowed regions over the history of the moon going back 4.5 billion years. And there are other hypotheses that state that maybe these distributions of ice might be within the top 50 centimeters due to remobilization of the ice and continually remobilizing it down to deeper and deeper depths. And so we'll be able to test those hypotheses. And in addition to that, we can verify the results from previous missions like Lunar Prospector and the LRO Lend instrument. So we'll be able to see these thick subsurface deposits, which may be pervasive at high latitudes. These are some hypotheses that were developed from the Dawn mission, which carried a neutron spectrometer to Ceres and looked at the distribution of hydrogen outside of craters, impact craters, and looked at the morphology that may be preserved. So we can test hypotheses about impact gardening, redistributing the ice around craters, as well as shallow ice like frost distributions not being necessarily consistent with the bulk hydrogen distribution. So we can test those, in particular at these regions that I've shown in the arrows. Is hydrogen enhanced in these regions? And can we test some of these hypotheses about ice stability at the South Pole of the moon? And then in addition to that, help plan future robotic explorations of the moon, in particular the Viper mission, which is a rover that's trying to pick a landing site at the South Pole of the moon, and our measurements will be at that scale. So that's sort of a brief overview of the science mission. I wanted to just talk briefly about the spacecraft. So this is the spacecraft, again, the size of a large shoebox. Our batteries provide, actually this is an older chart, we now have around 100 watt-hour battery. The mass of the spacecraft is just 14 kilograms total. And we're using a propulsion system. It's an ion propulsion system. I have a picture of it a bit later. It uses a solid iodine block that we vaporize and ionize out the back of the spacecraft to provide less than 1 millinewton of thrust through the duration of the mission. We use the same deep space communication transponder that was used on Marco, and a command and data handling system from Blue Canyon with a star tracker, antennas, all the things you would see on a big spacecraft just shrunk down. The other element of this mission that was somewhat challenging is we did not have a neutron spectrometer that would fit within a CubeSat of this size and provide sufficient efficiencies over a 2-month mission that would allow us to make those maps. So there are crystals out there, scintillators they're called. They produce a light flash when a neutron interacts in the crystal. And there are crystals out there that we were able to procure and build. So as part of this program, we also have developed an entirely new neutron spectrometer for small spacecraft. And we called it a miniature neutron spectrometer, but honestly, it takes up about 1/3 of our spacecraft. And it's about as big as other neutron spectrometers that have flown on traditional NASA missions. That's because our mission is relatively short, and our entire spacecraft is devoted to carrying one instrument. So we did, however, follow the CubeSat mentality in that this instrument is modular. So you can see here in the middle, the detector is made up of 2x2 arrays of these small modules of the scintillator material. And so the modules are commanded by 2 analog and digital boards that provide all the high voltage and command and data handling for the instrument. And if you had a smaller than LunaH-Map satellite or a larger than LunaH-Map satellite, you can build up large arrays of this material to accommodate your satellite, all your science mission, all within a CubeSat form factor. Although this instrument is large-ish for a neutron detector, it can be made smaller depending on the science mission goals. The instrument was designed, built, calibrated all within the scope of this program, and we calibrated that at Los Alamos. There's a neutron free and air facility. It's a big open room which simulates the deep space environment, and you use a calibrated neutron source to characterize the spatial response of the detector as well as the angular efficiency of the detector. It's the same facility that they use to calibrate the Dawn neutron spectrometer as well as the Lunar Prospector neutron spectrometer. So this is our science team and engineering team at the calibration facility in late 2018. You can see the neutron detector on a rotational stage, as well as one of our graduate students, Lena Heffern, who's on the team, helped me with some of the calibration. Okay, so I'll just go through a whirlwind on some of our hardware. These are our solar panels. These are the flight solar panels. If you're ever visiting or walking to work in ISTB4, you can see our little section of the 100K clean room. These solar arrays typically are not deployed. This was our first deployment test upon delivery in February last year. But I'll show you a picture later of all the hardware that we have in the 100K window. So just right near the elevators, if you're waiting for the elevators, look to the left, you'll see a lot of our hardware. This is our flight radio, the Iris, the same one that was sent. It's actually an upgraded version of the one that was sent on Marco, including our signal amplifiers, as well as the antennas. And then this is the real technology that's very new for our mission. This is the BIT3 propulsion system. That's our actual flight unit on the left. That's our actual flight unit firing in a thermal vacuum chamber at Busick earlier this year. And you can see the plume in the lower right that provides the thrust. And so this unit had to be characterized as well, a special thrust stand that measures the amount of thrust that's generated from a very small unit like this. Again, that's sort of the size of a tissue box that you'd see on your desk or at your house. It's very small. And so that's been characterized for hundreds of hours at this point in terms of the performance, and it's what really enables the mission. It also has a gimbal thruster. So we didn't have room on our spacecraft to what's called desaturate the momentum. So as you change your orientation on your spacecraft, you build up momentum inside. And on Earth orbiting spacecraft, you can desaturate that in a lot of different ways. You can have a little tiny propulsion system that shoots in different directions. You don't need much fuel to do that. But on Earth, it tends to be done with magnetotorquers. You use the Earth's magnetic field to rotate the spacecraft in different ways to desaturate any momentum that you built up by pointing the spacecraft in different orientations. And on our spacecraft, we don't have the ability to do that. So we gimbal the thruster during our very long thrust arcs to desaturate the momentum from the spacecraft. And just to, again, give you a sense for how big this is, they, for some reason, let me hold the thing. And that's me just holding it in their clean room prior to delivery of the propulsion system. Should never let the PI touch hardware. It's always a bad idea. And then this is what it looks like if you look in the clean room. Actually, it probably doesn't look like this anymore. It's a little bit of an old photo. But we're working with a small company, AZ Space Technologies, to help us with the integration of the spacecraft as well as the testing of the spacecraft and eventually delivery to NASA, which will be in late this year, early next year. And we're also using the shared Mission Operations Center that you're familiar with in the first floor when you walk in. So we're partnered with two companies, Qualtech and Kinetics. Qualtech specializes in mission operations and systems engineering. You may see Patrick and Tyler around. They are developing all of our ground data systems and operations tools that will help us talk to the Deep Space Network at JPL and send our spacecraft commands. And we are in parallel working with a company called Kinetics, which is based here out of Tempe, to build all of the mission navigation tools that we need. So building all of those long propulsive arcs that we need to get ourselves into orbit around the moon. And Kinetics is no slouch. They've been doing the navigation on New Horizons, as well as the OSIRIS-REx mission. So they're very familiar with mission operations and are a really great partner on this mission. So here's the propulsion system again, just to show a little bit of a cartoon on how we plan to gimbal the thrust so we can get 10 degrees of momentum management. And again, the Mission Operations Center, I think that slide just slipped in there somehow, sorry. Okay, so here's our mission design. We intend to deploy from the SLS. You can kind of see that in chart number 1. We deploy and then we actually execute a maneuver to target a lunar flyby. So within 48 hours of deployment, we need to execute our initial maneuver that will target a particular window around the moon. And if we hit that window, we'll fly out to what's called the weak stability boundary, which is the Lagrange point between the Earth and the Sun, where the force of gravity is approximately 0. And that's great because it allows us to turn around using our very weak propulsion system and eventually meet back up with the moon. And you can see in number 2, that's called the spiral down phase. Once we're captured by the moon in a high altitude circular orbit, we then spend the next series of months executing very long propulsive maneuvers to bring the spacecraft down into the science orbit that you see in number 3. I won't go into too much detail. This is some of the trajectory charts. That's what I just talked through. So 24 hours between deployment and thrust arc. We've actually since loosened that up a little bit. So we have around 48 to 72 hours to execute that maneuver. Sorry, it's 48 to 48 hours to execute that maneuver. So not a whole lot of time to get ourselves to target that lunar flyby. If we do miss that lunar flyby, there are other opportunities. So SLS, we would wind up in heliocentric orbit, and there are opportunities to do an Earth flyby that would get us back to the moon. So all is not lost if we don't meet that window. And here's just some more details on that spiral down orbit. And then the getting into that low altitude parallel orbit is sort of this phase here. So there's a lot of propulsive maneuvers to get us into the final science phase. Depending on the Earth, Moon, Sun position for when the Artemis 1 launch occurs, this portion of the mission, the cruise transition into the science phase, can take anywhere between 6 months to a year. So we're subject a little bit more than other missions to the tug of gravity from the Earth, Moon, and Sun and the deployment time. So just because our propulsion system is so weak. And so for our science measurements, which will just occur over the South Pole, we're screaming over the South Pole at about 2 kilometers a second. And so we pass over this entire study region in about 10 minutes. And so every orbit for about 30 minutes, we'll turn the detector on over the South Pole. For the rest of the science orbits, we'll do data tracking, we'll do Doppler tracking, as well as periodic maintenance on the orbit. So the orbit does need to be trimmed every 5 days or so, just to make sure that we don't either escape from lunar capture or crash into the moon. So again, that depends on the Earth-Sun orientation. Okay, so that's sort of the mission, where it is. Where are we now? This is just from our overall schedule. We've been integrating like all of our components. We've been in test. We've gone through vibration testing. You can see our delivery to Tyvak is the integrator that's performing the spacecraft integration for NASA. That is currently scheduled for mid-January. And SLS launch, you can see there is November XX. I think there's a launch date announcement forthcoming, but currently the best case or best scenario we've seen is to plan to a launch in November of next year. And so here is LunaH-Map. This was a big moment for us. Our final solar array integration happened in April of this year. And that's it, sitting in the box on the right side, everything fit in the box. We built the spacecraft, we completed the assembly, and were able to take the spacecraft into vibrational testing in May of this year. So I don't want to dwell too much on some of the challenges, as you can imagine. Maybe I'll save it for Q&A. A new mission like this is very challenging. There's technological challenges about will it work? You're working with new vendors. There's what I already mentioned, we discussed, how do you evaluate risk on a mission like this? The small size is one element of it, but it's really not the biggest technological challenge. And the low-ish budget relative to other NASA missions. And really what happens there is it just comes down to people. People have to serve in multiple roles that they wouldn't normally be serving in on a traditional NASA mission, and that elevates some of the risk and it elevates some of the stress. Overall, we're able to overcome those challenges. It's really come down to how well we're able to mitigate the risks on this new technology at this point. And there's non-technical challenges as well. It's an entirely new program for NASA. NASA's figuring out how to manage a program like this. You know, it's hard to do something new. I think that's just a non-technical challenge, but it really is. It's difficult for all sorts of reasons that I'd be happy to have hallway conversations with you about. But yeah, it's an interesting program. And I really just wanted to end on, we've had a lot of student involvement over the years, and I was going through putting this list together for this last slide. Our students that have worked with us have all had really great success stories. There are now professional engineers either at NASA centers, at Boeing, at JPL, or at Raytheon. And so I've been really proud of the students that we've been able to engage on this program and see go elsewhere. And like I mentioned, we're working with students currently on the program. So it's a great opportunity for our students here in CC and in Fulton to get good experience working on a flight program. So I'll end it there. We have a Twitter account. I don't manage it all the time, and there's a full drone LunaH-Map that's available. You can print it out at that website. But happy to take any questions if I have any time.
Thank you, Craig.
Thanks.
That's great.
Thanks, Craig. Yeah, you got plenty of time, so we're good.
Great.
So
do you want him to read off the Q&A himself, or should the questioners ask the question?
Well, typically what we do is I'll read them off, and also if people want to ask a question, they can raise their hands. If they want to be heard, I'm also happy to open that up that way. So otherwise, I'll just go from the top with some of the written questions. So Jerry Moore asks, how does the small scale affect efficiency?
Is that with respect to the detector?
It's a question she asked very early on, so I think it's a very general question. To take it wherever you want.
Yeah. Yeah, I mean, I mentioned on the detector, so the detector has to be somewhat large for the size of our spacecraft in order to get the efficiencies that we need to make the maps of hydrogen at the South Pole. As far as the spacecraft itself, I guess I'm not entirely sure how to answer that question in terms of how efficient
Yeah,
we are in terms of all the other components.
yeah, she posted on the chat that she was asking with respect to the device itself. So not the detectors per se, but that's fine.
Yeah, I'm more familiar with the detector and the efficiency and how we scaled things on the neutron detector side, and it was somewhat challenging to make a detector that efficient.
Right. Well, it's okay. So let me keep moving on then. Oh, wait, there's more. Size of craft versus engine equipment weight size. So she posted an additional follow-up. So size of the spacecraft versus the engine and equipment weight.
Yeah, it's funny. I think there are almost no propulsion systems. I'll just talk for one component. There are almost no propulsion systems that I'm aware of. I saw somebody in the chat is developing one, and they are all being developed as I understand it, and they're at different stages of development. So in our case, for the Delta V requirements that we had on this mission to be captured by the moon with a deployment from the SLS, we had only one choice. So our trade study wasn't all that long, and so it was go with that or you can't get to the moon. In some other cases, one other brief story was about the batteries. So we did, we have solar panels. They're relatively large for the size of the spacecraft. They provide power to the propulsion system. We had at some point the ability we actually had space on the spacecraft, and we thought, well, what could we add? And there was a push to add a camera, a visible camera. And we thought long and hard about it, and we went with batteries. So you add margin on the power system to put batteries in the spacecraft. So we don't have a lot of margin on some of these systems. There's, things are running pretty tight. So where you can add margin, you can. And so there were trade studies on various components, but for the most part, things are so new that there was often only one option for us to go with. So that's not a very satisfactory answer, but it might help.
Maitri has a question that shifts us towards science a little bit. Are there specific craters that could be completely mapped at the highest spatial resolution by LunaH-Map?
There are some pretty large craters. Amundsen is relatively large, several hundred square kilometers, where we would get a number of pixels within that region. Within the region around Cabeus, we'll certainly get multiple pixels as well. I believe Shoemaker, we should get a couple pixels, so you can start to discern enrichments in the upper left versus lower right quadrant. But you can kind of see on the maps I showed, we're mainly focused on resolving one PSR from another.
Question about hydrated minerals. Are there any hydrated minerals or other non-ice sources of hydrogen that will complicate neutron data interpretation?
Yeah, so there are other volatiles on within, I believe, that were kicked up in the L-Cross impactor, and I don't have the names of them off the top of my head, unfortunately. There's a laundry list of molecules, and some of them are hydrated. And I know that there had been some discussion about, well, how much was in the material that was in the impactor itself, but yes, there are volatile species that would be deposited by passing comets and asteroids that are hydrated. LunaH-Map won't be able to address whether or not the signal we're seeing is from hydrated species other than water or H2O, or even just molecular hydrogen. My understanding is the abundance of those species is not particularly high, even in the plumes that were kicked up. And the most abundant species was water ice in the L-Cross plume. So it's a reasonable proxy to use on our mission, but it's true, we won't be able to distinguish between any other hydrated species and water.
All right. Given the relatively small surface area of CubeSats, how does your team compensate for energy consumption versus energy gathering capabilities? How long can the Luna CubeSat operate before having to shut down in order to charge?
Right. Yes. So the operational modes on the spacecraft, we don't have very complex operational modes. If we're using the propulsion system, we are not in communication with Earth. We could turn the radio on for a brief period of time, but we're not doing, in most cases, we're not doing more than one thing at once. There are some instances that are very important for the mission. Those are some of the critical cases that I mentioned that we tested. So we do need to gimbal the solar arrays while we're acquiring science measurements. We do need to gimbal the solar arrays in some cases when we're in communication with Earth. So when the radio is on in transmit, we want to make sure that we have enough power. But the propulsion system uses about 65 watts of power when it's on and thrusting. And so the batteries are not intended to allow us to thrust for much time at all. If we're doing that, we're likely in an eclipse. If we're in an eclipse, we're likely not thrusting. So the propulsion system is powered directly from the arrays themselves. And so the arrays were scaled to power the propulsion system and the other subsystems that needed to be powered. So the reason those solar arrays are so large is so we could get up to 95 watts at the beginning of life, so that we could power the propulsion system with 65 watts, keep the flight computer on and the reaction wheels on, and the radio on in receive. That's it. And so all of that was scaled with sufficient power margin to perform that activity. And from there, all of the other activities that the spacecraft performs are much lower power than that. That 65 watt propulsion system is the power driver on. That probably helps answer the other question. But yeah, that's the reason the spacecraft looks like it does is to power the propulsion system with that's the high power driver.
All right.
Does that answer
that? I guess.
Okay.
I think so. You
Normally I would ask that in an in-person talk and get a head nod or something.
Right. Yeah. So that's something that's lost here. So this may be the last question, depending on time. So Steve Ruff asks, is there another reasonable explanation for the LEND non-PSR high H detections other than ice? Noise. So there have been a lot of studies on the LEND data, and there's a collimated portion and there's a non-collimated portion. If there's a detailed study that came out several years ago looking at if you populate the south pole of the moon with a distribution of hydrogen like what I showed in the slides, a reasonable distribution, and you then factor in how many neutrons you would get just with random noise from an uncollimated detector. They were able to reproduce to within a reasonable statistical measure, the LEND collimated results. And so that lends some evidence that perhaps the collimator is not working as well as they said it does. That doesn't mean the LEND results shouldn't be believed. The uncollimated results are likely just fine, but the collimated results, interpreting any one small spot might be problematic. So hopefully that answers your question, Steve. I think that's the going thinking on why there are some enrichments outside of PSRs in the LEND data. I just add that with the Lunar Prospector data, there are also enrichments outside of PSRs. So it could be real. We don't know. All right. Well, that sounds great, and we've reached time. So, Craig, I want to thank you. Thanks for a very nice overview, great accessible talk. Thanks, Jim, for introducing. And just a word to everybody. So next week we shift from the moon to Mars. Nick Schneider from University of Colorado will be giving a presentation, Surprises from Maven at Mars, Aurora, Meteor Showers, and a New Water Loss Paradigm. So water on the moon to water on Mars. So hope to see you here next week. Thanks again, Craig, and thanks all of you for attending and for all the great questions.
Thanks, Craig. Well done.